and then we'll discuss the coming demonstration on the software that is called Nanodecals. So let me share my presentation screen. I hope my presentation is visible to all the participants.
No, sir.
Is it not visible right now?
Now it's visible.
Okay.
Sir.
Yes, sir. Yes, sir.
Great. Thank you. Thank you for the confirmations. So let's start the second day. Let's start the second day of the sessions. So yesterday we discussed about this Rescu software. That was basically for materials specific applications, response functions, electronic properties, Phonon properties, and this Raman and optical calculations. Now in today's session, we will discuss about the Nanodcal software. That is basically a density functional theory simulation tool, as well as NEGF, the quantum transports NEGF from first principle ab initio will be discussed today. So these are two software. One is called Rescu for material, and this Nanodcal can work on material as well as the device applications. And the quantum TCAD tool for spin qubit in semiconductor device simulation will be discussed by tomorrow. So if you want to work on latest technology, quantum qubit simulation, you can attend the session and tomorrow at the same time, 5 p.m. from the same link. So let me start my session. I want to continue. So as you already know about the nanoacademic technology, which I already discussed yesterday, about this Rescu software for DFT and perturbation theory solvers for large number of materials specific application. And I already discussed in detail. If somebody not attended our webinar yesterday, they can also get the recording of the videos, which is available on our YouTube channels. Now, today's session, I want to discuss on the Nanodecal code. Nanodecal stands for Nano DFT calculator. Okay, so this will also works on the density functional theory, but the basis sets will be lesser as compared to the Rescu, because Rescu will have more advanced theoretical parameters. But in this Nanodecal was basically developed for device-specific applications, transistors-specific applications, and also they can also simulate some basic parameters of material characterizations. So material simulation, device simulation, transistor simulation, two-terminal, three-terminal, or multi-probe device structure can be modeled and simulated. So this is also like we offer the Rescu and separately, Nanodecal separately, and Nanodecal plus Rescu as a bundle package to the audience, those who are interested. Now, this software Nanodecal will work on DFT as well as non-equilibrium gain functions. So the quantum transport theory is also implemented in this software. Now, you can find there are so many publications will be there by using this Nanodecal software in good journals. If you simply type Nanodecal, this one code keyword on the Google Scholar page, you can find a lot of publications. And it focus on basic material characterization, device simulations, IB characterizations, including electronic, spintronics, and gate-related transistor characteristics. All the spintronics capability is also there with the device-specific analysis. All electronic DOS, PLDOS, LDOS, PDOS, band structure, Bennier functions, and some bend and folding, and many other analysis, including thermal transports calculations. So transports, electronic, molecular electronics, as well as some device-specific application, the software can simulate. Now, let me come to the details part. As in presentation session yesterday, I discussed about the top parameters in Rescu for molecular surface on different planes, some Miller indices in this surface structure, complex materials, the Rescu and Nanodecal, and interface, both software can work for. But when you work on device-specific applications, let's suppose you want to simulate some device which is having some anode and cathode, or top and bottom electrode is there. We can call anode and cathode. So that kind of device you want to simulate, wherever you want to apply some biasing on the terminal, and that biasing you want to characterize how much the current will be calculated based on this analysis, the IV current, thermoelectric currents, conductance analysis, photocurrent, and some transmission spectrum, and many other electrical transmissions, and that magnetic property can also be calculated. So based on that molecular material-based device, you can model and simulate it. 2D material-based devices can be simulated, or any complex material-based device you want to build and simulate, it can also get it simulated. So material as well as device can be both simulated in this Nanodcal code. Now, if we talk about the same thing, the material analysis and device analysis, there is a user interface which you already seen yesterday that can help you same for the modeling purpose for the device applications also, and the DFT parameter for the NEGF Hamiltonian equations that will also be there, where you can select some Hamiltonian parameter. And if we talk about the analysis, yesterday I shown you some material related characteristics. Now, if here you see the properties for the material and devices, then you can see the density of state, effective potential, total energy, scattering, transmission, photocurrent, IV curve, charge, electron density, potential, conductance, thermoelectric current, Seebeck coefficient, AC conductance. So DC conductance, AC conductance, thermoelectric current, Seebeck coefficient, ZT, and many modulus and other material characteristics will also be there. So right side, there is an analysis part of the crystal, and this is a part of the device specific applications. So both tools are very strongly can help you to characterize accurately your materials behavior, and then the device can also be modeled, and you can also simulate and analyze the device properties. So material property is also there, where ZT, phonon, modulus, force, stress, band structures, and the device spectrum and device analysis is also there. So it is a complete package in single software where all the type of applications can be simulated. So many people works on different applications. So whatever type of application you are working on, or your group is working on that, then you can use this software for multi-domains specific research. Now, if we go into the next slides that discuss about the spintronics, apart from the nanoelectronics applications, basics nanoelectronics, nanotechnology, crystal material device application, if you want to work on spintronics application, then next generation nanoelectronics for lower power consumption devices, the spin type of devices can be simulated as well. Spin type of material, the movement of your atomic position, atom spin up, spin down of your atomic position movement, that band gap EK diagram in respect of spin up, spin down, and both the condition you can plot. You can also make some graphene structure. You can sandwich some graphene nanoribbon or electrical fields you can apply. Spin orbital interaction will be there, and some rho theta phi magnetic movements. So all the related to spintronics, whatever the input parameter you could be enabled. The software having its own interface where you can select your desired input, and software will run the calculation based on your input selected, and it will run the job and give you the prediction of your analysis. Now, if many people works on single layer structures, like let's suppose you are working on single layer of graphene sheets are there, and that you want to simulate. So there will be a full provision where you can simulate the single layer, and if you want to create some defect by delete particular atom or creating any structural defect, so single layers can be simulated. If you want to create some buckling in that, or some twisting in the layers, so the twisting can be created, buckling can be created, or whatever the manipulation in your structure you want to do, that manipulations can be done. Apart from that, if you want to simulate a bi-layer structure, some two layers are there of the graphene or any other materials. So as in this particular case, there is a boron nitride layer on the top side, graphene layers on the middle of the region, that is sandwich in between two boron nitride layer on top and bottom electrode. And if any participants have any questions, you can unmute your mics, and I am not able to read your chat box basically. So this magnetic movement, magnetic properties, spin up, spin down related calculations for single layer or bi-layer application, you can get it simulated. Now, spintronics, nanoelectronics, as well as molecular electronics domain, the software can work for the two-terminal as well as the three-terminal devices. So if you have some, like let's suppose one molecular structures, and this particular, in middle of this region, there is one green layer. That green layer is made with a molecular layer, and this is connected with metallic gold electrodes. And there is some gate is also there, with the dielectric constant of the gate is also defined. So based on two different molecular materials, you can take it and you can connect with the metallic material. So in this particular A and B graph, the two different molecular structures are taken and connected with the gold electrode, and accordingly the transmission spectrum were calculated. So this is one of the paper published where you can use the multiple type of scenarios, multiple type of manipulation in your structure you want to do. That will be the full capability the user can do according to their needs. So molecular specific domains, it can also works. So this software basically not only works on material specific application or molecular specific application. Many people have restrictions in terms of only crystal can be simulated, or only molecule can be simulated, or only crystal and molecule can be simulated. There is no full privileges where all the type of applications can be simulated. It is one of the specific software which coupled with the multi-domains applications. Either you are working on crystal, or you are working on molecular structures and any nanomaterial, or two-terminal based devices, anode and cathode, or even the three-terminal based devices, four-terminal based devices, even up to six-terminal, where six probes will be there. The user can define up to six probe and you can get it simulated. Like if you see, this is one of the structure where there is some one vertical carbon nanotube and horizontal carbon nanotube in 2D. Or we can also take the graphene and we can rotate on different angles. So flexible electronics domains, those who work on that, so that can also be works on flexible structure simulation, where you can rotate or bend your structure on particular angles. So that angle radiations, that radius of particular thickness, you can rotate particular elements, and then you can also simulate some flexible electronics devices. So material specific domains, DC-AC conductance, IV characteristics, photocurrents. So up to 6 probe device structures, you can easily simulate based on first principle, ab initio, linear combination of atomic orbital for electron transports calculations. Now, as one of the participants yesterday asked about thermoelectric properties, so I want to assure you, I want to promise you, yeah, the software can also able to calculate the thermoelectric property of the materials, as well as some device properties. So if you want to calculate for power generation application, thermoelectric material for transforming the heat into the electricity. So these thermoelectric materials are able to simulate with different temperature. You can vary the temperature range, and based on different temperature, you can simulate your material or device and find some thermoelectric properties. Like if you want to calculate the thermal conductivity, you want to calculate the ZT, you want to calculate the conductance, you want to calculate the CV coefficients on different temperature. So that analysis can easily be done by any of the users. So this thermoelectric analysis is also possible in the tool. So whatever, if you want to do the research, there is also the functionality can also be enabled. And even those who also works on photodetectors application for two-terminal bandgap semiconductor devices, for light absorbing devices. So the UV lights with the photons, the incoming photons can also be fall on your device on the channel region in between the electrodes, and you can find the photocurrent of the device structures. So this first principle, ab initio, spin-orbital coupling, spin-orbital interaction, non-collinear electron-phonon interactions. So this whole different kind of light can be fall. Circular polarized, elliptical polarized, or other combination is also there for illumination the light on your device. So that can detect your photons, and that photo detectors can be simulated, and you can plot the photocurrent and other characteristics. Now this is basic idea about the device specific applications. Now we will discuss into the detail how it can be done inside the softwares. So the presentation is just to give you the overall idea that what software can do and how it can be done. That will be demonstrate you shortly. Even if any participants have any questions during the session, end of the session, or later this finishing of this FDP program, you can send me the email or you can call me or email me. So this is my contact information. So participants, if you are interested to discuss directly or you have any requirement for such kind of software, commercial software, you can drop an email or you can call us. We can try to help you so that you can technically satisfy its capabilities. So today's session will discuss about Nanodcal software, and other session will also be there on specific to perovskite applications, quantum technologies, solar cells, experimental characterizations, and advanced capability of this Rescu and Nanodcal Plus. So this I request to all the participants, please stay tuned for 5 days, and I believe you will get to know many innovative things, innovative topics that will be discussed with the commercial industry level software as well as some equipments. So once again, thank you for listening the presentation session. Now I will start by demonstration on the software part. So I want to open the software. So I would like to start the software from beginning. So let me open my software wherever I have installed. So I want to open my device studio. This is my device studio. That is the user interface, and that will help you to model the structure and run the simulation and visualize your output. So I want to open this device studio. I would like to double click to open the interface. Now here, if you see there is one welcome window of device studio. If you want to start from scratch, you can also create the new project. So I selected create a new project and click on OK and save the path. So let me give the path name of the project FDP day 2. This is my project name, and then I want to save on my desktop. So this will save on desktop, and then I can maximize it. Now, since yesterday I discussed few of the user interface parameter I shown you for material analysis. Now, since we have a lot of many things are there, so I want to explain some other things. I believe this could also be benefited for device related applications. Now, I want to click on the file option, and as I explained yesterday, there is option called import. So either I can import from my library or I can import from online database. So we have the capability dependent on the requirement. I can choose it. Let me try to build one device structure from beginning. Okay. So I want to click on this import local button. And then I want to choose the material, that whatever the material I want to use it, I can take that materials. Just a minute. I can take one example and I will try to start from scratch the modeling parts. So let me take it. So this is one of the structure, which is device structure. I will try to model this structure in front of you. Okay, this is one of the structure that is all automatically already given in our library in the example parts. So I will try to model this structure live in front of you. So first of all, I want to take my material. So I want to export this alkyl molecule. Okay, so I will try to create one device structure from scratch. So this is like my empty project. I want to create from big. So first of all, I went to the import and then import local, and I choose the material for the electrode part. So first of all, let's me import the gold material, which I will try to make as a electrode, as a metallic electrode. So this is one gold material which I imported. Now I want to redefine this gold material. So whatever the manipulation in this crystal gold material I want to do, I can do according to my needs. So this is one of the gold single crystal atom lattice parameter is there. If you want to see the information about this particular unit cell, then you can find this property bar in this left side. So in this property bar, you can see there is an option called vector ABC. So this is the vector ABC, total number of atom, total area of this lattice, and chemical formula of this lattice. Now, once it is done, you can see the information property of this particular selected crystal. Now I want to click on this build option and want to redefine my crystals. So if you see, there is an option called redefine. We have a couple of other options also. So based on our need, we can select particular features. Let me redefine this crystal. So I will click on this redefine, where I can define the crystal by expressing the new cell vector, the U, B, and W, as a linear combination of current cell vector ABC. So the UBW we can define as a linear combination of current cell vector. Let me take this F face centered. So once I click on this face centered and then click on preview, before building your final structure, I can see the preview in face centered of this gold crystal. Then I click on the build button. Now I want to make the supercell. So I click on the build button and then I will click on again on the redefine crystal. So to build the supercell, I want to repeat this structure. Let's suppose 2 cross 4. So in A direction 2, in B C, in B direction 2, and in C direction, I want to repeat this structure 4 times. So once I will define this 2 cross 4, so it will multiply 2 times in A direction, 2 times in B direction, and 4 times in C direction, and then click on preview. So it is repeated, whatever I mentioned, accordingly it has repeated. So we can see that structure from the interface. It will quickly make manipulation in your structures, and then click on build button. Now your supercell is ready. Now there is an option called home button. In the home button, I can click on XY view, XZ view, YZ view, YX view, ZX view. Whatever view I want to view, I can see this structure visualization from that particular view. So I selected XY view here, and I want to delete undesired atom because I want to make some electrode with a specific type. So I selected this top all 4 atom by drawing the rectangle. All 4 are selected, which is showing with the light yellow colors. And then I will press the delete button. It will delete my top electrons, top atoms. Similarly, I want to delete this right side, all three atoms. So I selected all three atom and their other atoms in their G directions. So that all atoms I have selected, and then I press the delete buttons. So let's suppose I wanted to delete some of the atom, and so if you can also follow the similar procedure, and according to your need, you can visualize on any angle and delete the required atom if you want to delete. Now then I want to click on ZX view. So on different angle I want to see my structure. So this is like ZX view, where I want to, let's suppose I want to select these all atom by drawing the rectangle, and I don't want to delete this atom. So I press the control button and deselect this particular atoms. Now these all atoms, this all 5 atoms, and behind that all the atoms are selected. I can press this delete button to delete that selected atoms. So this particular type of shape I wanted to create, and now it's created. Now if you see, this is particular type of structure which I have created for this gold electrodes. Now I want to make some vacuum inside this unit cell. I want to create some vacuum. To create the vacuum, there is an option called convert to crystal. So this option, once I click on this toolbar, this convert to crystal, there is also other provision where I can convert this crystal to cubic simple, cubic face centered, cubic body centered, rhombohedral, hexagonal, tetragonal body centric, orthorhombic, and multiple type of orthorhombic, monoclinic, triclinic, and user defined brevis lattice is also there, and the user can select according to their needs. But initially I want to add the vacuum in this unit cells. So let's suppose this XA is equal to, I want to create 20 angstrom the space. So you can see here the space has been created in A direction. The vacuum has been created. Similarly, if I scroll this is a scroll button where I can scroll top and bottom, and this B button, that is by, I also want to make some space, so I can make it 20 also here. Now B is vertical one, so vertically the space is also created. So A and B, I have created the space in the vacuum. The vacuum has been created in this unit cell, and then click on build button. Now this is one of the structure where vacuum is created. You can view on different angles, whatever the angle you want to view. The visualization can be done on that particular angles. Now once it is done, I want to make it center, because right now it is not in center. I want to take this in the center positions. To take this structure in the center position, there is an option called center along A, center along B, or center along C. So since I increased the A and B vacuum in this unit cell, so I want to make it center along A axis, and similarly I will click on center along B axis. So the position has been center of this A and B for this particular crystals. So this is the center position. By single click, we can change the position of our atomic structures. Now, once it is done, then we can import the molecule which I want to make the device, which I want to connect with this electrode. So I click on the file option and then click on the import option. Let me import locally in my database. And I went to the desktop where this XZW file is there, alkynethyl. I selected and it is now imported. So we can also import any material by following the same procedure. The material can be imported. So this is alkynethyl molecule where hydrogen atoms are there on the top. So this white color atoms are hydrogen atom, and this one is called the carbon atoms, and this yellow one is called the sulfur atoms. This makes the one molecule, and if you want to take another molecule, you can choose according to your particular need, but I want to make this, so I have selected this one. Now the molecule has been added in our dashboard. So this is one of the electrode and this is one of the molecular in the middle of the regions. That is called the center region. And to use this metallic electrode, let me use the same material in the right side of the electrode also. So left electrode and right electrode, as an example, I want to use same material. So what I will do, I will select this particular structure. So by drawing the rectangle, all atom will get selected. So I draw the rectangle, it will get select by pressing the hold button. And then I will click on this mirror atom. So as you know, this the NMOS may have some same electrode on top and bottom or left and right. Similarly, I can choose the left and right will have the same gold electrodes. So I select here and select the lattice vector. That let me choose XY lattice vector. That is 0, 0, 1. And the distance which I can want to create the mirror. Let as an example, I want to give 6.7105. This particular space, I want to create the mirror of the same metallic gold electrode and click on apply. Once I click on apply, you can see here the same electrode has been created in the mirror form. So mirror of this with the distance of 6.7105, whatever I mentioned, that particular distance, the mirror has been created. Now, once the mirror is created, and right now this crystal is not inside of this unit cell. I want that this should also be inside of this unit cell. So I want to increase the vacuum. I want to increase the vacuum of this unit cell. So to increase the vacuum, I need to click on the convert to crystal button on the top of the menu. So this toolbar is there where I can click on convert to crystal, and I need to increase the G direction, the C transport direction vacuum. So this is like G direction where horizontally I have to increase this lattice space. Lattice vacuum need to be increased. So let me define the value of Z space. So as an example, I want to put it somewhere around this value so that it will create the same error without lattice mismatch. So once I done it, you can see both the electrode are in same box, same lattice. So that's why we can try to form the device. So it is inside of this particular unit cell and click on build button. Now in between these electrode, this is metallic electrode in the left side and right side. I want to connect the alkylmethyl molecules. So to connect the alkylmethyl molecule, I have to select this alkylmethyl molecule. And I will drag the rectangle, draw the rectangle to select all the elements and press Ctrl C. Ctrl C to copy this particular molecule. And then I will click on this material HZW file and click here, paste buttons. So once I click on paste, the alkylmethyl molecule will be copied from here and it will paste in this particular structures, in this particular input files. So that particular molecule has been copied. If you want to visualize it, you can see this is the copied structures. This one is the copy. Now you have to connect this molecule in between this electrode and this electrode. For that purpose, you have to select first of all the So first of all, you have to select the molecule which I have copied right now. And then I will press the center button. So this there will be a center button which I can, the selected molecule will be in the center of these positions. So once I click on it, it will move that position and it will reach in the center of the position of these crystals. So if you see, it is now connected, the crystal molecule has been connected with the metallic electrodes. So this is one of the example which I'm telling you. There are a couple of multiple ways where user can create according to their needs. Whatever other molecule, whatever other material, whatever other lattice type you want to take, you can take the help of this particular interface, and any complex materials can be created very quickly. So you can save a lot of your time in modeling the part. Click on the home button. Now it is connected, and this is the material where metallic electrode and molecules are there. To make the device structures, right now we have not made the device. So we have to convert this material into the device. So to convert into the device, we have to click on this convert to device options. Either we can convert, click on this right top convert to device option, or we can also go to this build option and convert to device options. So dependent on your needs, this window will pop up. This dialog is for multi-electrode device. So the device which is having multi-electrode, left electrode, right electrode, top electrode, front electrode, back electrode, or top bottom electrodes. So wherever the electrode position is there, you can select the position of the electrodes, and accordingly you can select the electrode, either it is left type or it is a right type. So I have selected the electrode, and by default the algorithm will select the thickness of the electrodes. So you can click on the default thickness if you want to increase or decrease the thickness of the electrodes. So this is the thickness, this left side and right side. By default, this one is showing here. This is the thickness in the left side, and this is the same thickness in the right side. But if you want to change, it is a complete provision is there where you can choose according to the thickness, your need, you can customize the thickness of the electrodes. So if you, let's suppose you want to take 6 point something, then you can make it this particular type of thickness can be increased. So left side has been increased as compared to the right side of the electrodes. So dependent on your needs, you can choose the thickness of your metallic electrode material, and then you can click on the build buttons. Now once you've done this build button, your device, 2-terminal device is ready. 2-terminal device is ready where left side electrode is there and right side electrode is there. Now to generate the required input files. So to generate the required input file, you have to go to the Nanodcal. We also have the AI relaxation, which can relax your structure. Yesterday I discussed about this Rescu software. As you know, the Rescu works on material applications. Since the device is created right now, that's why the device cannot be simulated by using Rescu, because it is only for material related applications. But this device, mostly all features are enabled. This feature will be enabled for multi-mole fractions or some compositional waste analysis. Whenever you will do compositional, then this virtual crystal can also be enabled. Now you can see here, this is FCF calculation, relaxation, transistor, IV curve, analysis, transistor plot, various other features are there. So I go to the Nanodcal and click on SCF calculations. SCF stands for cell consistent field. For this particular structure, it will select the desired DFT parameter, NEGF parameter, and default biasing parameter, basis sets, spin type. So all the parameter, whatever required default, it will take it. But if you want to change it, you can also change according to your needs. Now this is electron temperature, energy cutoff, and some exchange correlation functions, LDA and GGA are given for the device related applications. And sampling point are there, N1, N2, N3. You can select the sampling points, and electron temperature in Kelvin, energy cutoff in Rydberg, Harty, or electron volt, whatever the unit you want to take. You can choose particular value and you can use it. Then contour integral is there, integral, lower bound, contour integral, circle point, real axis point density, real axis infinitesimal, and this electrode is there. Yesterday this electrode function and contour integral were not available. When I was simulating the material, the electrode options were not there because the Rescu do not works on device related applications. That's why the electrode were not there. But here, whatever the voltage you want to apply, you can apply the biasing on the voltage. And you can apply here, let's suppose, whatever the biasing. Initially, you can simulate at equilibrium. Then you can apply some voltage biasing of 0.1, 0.2, 0.3, 0.4. Different voltage biasing you can apply, and you can also simulate on different biasing, applied bias. This is iteration control, where it will solve the density matrix, Hamiltonian, total energy, mixed wave, iteration methods. Basis sets are there. Default, it will select some basis sets. So double zeta polarized LDA type for each material: gold, carbon, hydrogen, sulfur. Each element, the basis sets are selected. If you want to enable Howard U, then this LDA plus U is also there. SPDF you can define. And there is also provision for doping. If you want to add the doping, this doping can also be created, and you can use doping on particular regions. And then there is one of the tab where you can select the type of spin: collinear spin, general spin, or without spins. So this spin type effect, if you want to include, because spintronics may take some time in the simulations, and general spin is also there to include the spin orbital effect. So electron phonon interaction is also there. I want to initially simulate without any spin effect. So I select no spin and click on generate files. Once I click on generate file, you can see the folder has been created where you can visualize the device 1, electrode, that is left electrode, right electrode. In the electrode option, there is SCF input file is there. In the left electrode folder, SCF input file, right electrode SCF input file, and device 1 SCF input file. So if you want to check the input file script, you can right click and click on open with. It will show the script that is automatically generated by the softwares. So all the parameters, SCF parameters, temperature parameter, energy cutoff, LDA, sampling point, vectors, if any spin effect is included or not, or iteration control parameters, or even the element name and element coordinate point and their basis sets, number of elements in the left electrode. So these all information are there. This is basically for left electrode. So you can run the simulation. You can right click and click on the run button and click on this run program. Similarly, the right electrode is there. You can also open the right electrodes. So left and right electrode both are same materials. Okay. Because left is also gold electrode, right is also gold electrode. So either we can simulate one of the electrode and we can use in the device, or we can also simulate both electrode one by one. So this is 2 electrode, left and right electrode, and then main input file. This is the main device input file. So output of the electrode will assign in this device main SCF input file. You can see here, this is the left electrode output data, MATLAB output data, and this is right electrode MATLAB output data. And whatever the electrode biasing applied, that will shown here. So this is a final device input file. This is a device folder which you can see. Inside that there is SCF input file. It contains all the associated files. So that's why the electrode left and right electrode output will also be called during the simulation in this main SCF input file of the device. So you can see here the calculation is running. Initially it is running for the left electrode. So in the bottom bar, job manager page, you can see the simulation is running here. The simulation, as you know, the live calculation will take some time. And in the meantime, if you want to run the device 1 also, so you can select the device and you can run it. And see here, the simulation is running. Once the first one finish the calculation, then second will start execute right electrode, and then the main device start will execute. So this is the device and electrode. Now, if we talk about the analysis part, what kind of material property or device property the software can predict. So I will go to the Nanodcal and go to the analysis options. In the analysis option, you can see electrode type. So first of all, let's suppose you want to select the left electrode. So this is left electrode analysis. In the left electrode analysis, let's suppose you want to select the gold material band structures. So I selected the band structure. This is the symmetry K points, G and X. This is the sampling number of K points. So you can see this is symmetry points, G and X. You can add or delete the high symmetry K points in billion zones for this band structures. So if you want to add the billion zones band structure, high symmetry K points, you can also add that. Similarly, if you want to see the effective potential, it will also be added. If you want to see the electron density, if you want to see the potential, transmission channel, or these all analysis, these are all material specific analysis. Whatever the analysis for this material, by using Nanodcal, you can choose your required analysis. Out of all, I have selected 5 analysis points. So electron density is there, charge electron density, total electron density, neutral atomic density, and many other potential is also there. So whatever type of band structure you want to plot, you also have that provision. Similarly, the density of state is also there. If you want to select the density of state, local density of states, so you can choose that particular points. And now I will click on generate files. So for this electrode of the gold, it will run these input file has been generated. The input file has been generated. The second input file is running or executing. You can see the electrode has finished their calculations and device 1 is executing. And there are total 76 atoms are there. And if you want to run this band structure analysis, so you can run, before running device, let it simulate the material, then we'll run the device. So I want to stop the job for the device input file. So I click on the device input file and crash it, because I wanted to run the band structure.input file. So that all electrode material property I want to calculate first, and then we'll make the device properties. So I selected this electron density, band structure, effective potential, transmission channels, density of states. I have selected all my input and running in the background. So that's why you can see in the backends, the simulation for the material, it is running and finishing one by one. Once it is done, then we will run the device input files, because device input file may take some time. So that's why I thought that let it simulate the material property first, and then we'll run the device properties. So it is finishing quickly, and the output is also generating parallelly. Now all has been finished the job. I want to run the main SCF input file for devices as well. So I will click and run it. So it will run here. You can see like that. And if you want to select the device analysis part, I go to the simulator, Nanodcal, and then go to the analysis options. Now these are the device related properties. Density of state for the device, effective potential, total energy, scattering state, transmission spectrum, transmission type, photocurrent, IV curve, charge, electron density, potential, conductance, thermoelectric current, Seebeck coefficient, AC conductance. Whatever analysis you want to plot, you have to select that and it will plot that output. So I'm selecting few of them. Now this is like I have selected and click on generate files. So inside this device folder, whatever the analysis I wanted to do, all the input file has generated. I have to execute these input files. I will right click and click on the run buttons. So I'm running my all input file. The device will get it material property and device property will execute in the background. In the meantime, I will try to show you some other output, whatever we have got till now. So I'm putting my all input file in the queue so that it will automatically take in the queue. So you can see here the main device is running and other input file in the queue. So automatically it will take it consider. It will consider here. So as you know, the number of atoms are 76, which may take some little bit time, and I'm also running in serial calculation. So that's why the simulation time may be little bit higher. But anyway, definitely you will get some output, which I will show you today. So simulation is running here. Now I want to show you the output of the materials. So this is particular folder where if you see here, left electrode folder, you can find the XML and DXF file. So band structure, if I will right click on band structure.xml, right click and click on show view. So this is a data visualization where you can visualize your band structure for this gold electrodes. So you can see here the band structure has been plotted for the material first, and then device analysis will also execute and we can plot it. So we can select any particular element, particular line, or we can zoom whatever the zoom. And if you want to export your data, there is an option called file button. In the file button, there is an option called export image, export all data. If you want to export in the form of image, you can click on export image and save in the form of image of this data. And if you want to save in the form of, you can use the type of aspect ratio. And then if you want to use all export data in terms of text file, so the text file data can also be exported. So I selected that format and click on save button. It will export in that particular formats. So the data can be visualized and exported in that particular format for the band structure, which I have shown you. Similarly, if you want to see the other analysis, you want to see the total electron density. So I will right click on this total electron density and click on show view. So this is the electrode position, gold electrode, 3D model view is there. If you want to see the 2D analysis, this is two-dimensional total electron density, average along x-axis, along y-axis, along z-axis. So that axis, whatever the average direction, you want to visualize your total electron density, you can visualize in that particular plane. If you want to zoom that particular region, you can also zoom in. This is plane display. If you want to see stereoscopic analysis display, it can help you to get the data in that particular. So this is for electrode, gold electrode, the electron density is calculated. So with this particular, you can also take on different angle. 3D viewer is there, where X by view, XZ view, YZ view, YX view, or other view are there. Whatever the angle you want to visualize your data, it can be visualized. Similarly, apart from this visualization of options, there is also provision to export your data. So the data can also be exported. If you want to export, The data can be exported in PNG, JPG, PDF, TIFF, or EPS format. So these extensions, the data can be exported. Now, once it is done, if you want to analyze some other analysis, so what I have shown you, electron density in 3D graph. So in 3D model, 2D model, this is two-dimensional and one-dimensional. So one-dimensional, two-dimensional, and three-dimensional. Whatever the plane you want to visualize your electron density, it can show in this particular direction. You can plot 1D, 2D, and 3D. So all models are there. Whatever the convenient to you, you can choose it. If you want to see other analysis, this is like effective potential. This is effective potential. So you can see the effective potential of average X, Y, and Z. And same scenario, this case is also there. You can visualize with this particular label, and one-dimensional analysis is also there. So let me see if there is some density of state, because it is metallic, so maybe some issue. So all the whatever some of the analysis I have shown you, but as you know, the simulation for the main device is still executing. This SCF input file is still executing because the number of atoms are 76, which may take some time in the calculations. So still not a worry. It is executing in the background. But in the meantime, I can show you many other softwares. So like this is a two-terminal based device. If you want to make the flexible based device, you want to make the bending of the device. You want to bend the device on particular angle. Let's suppose left side of the electrode, right side of the electrode, or other positions. So you can click on this bending of the device. You can bend on 30-degree angle or 50-degree angle. So you can see the preview also at what angle it will build. So this is like a bending model. So it is bend the 50-degree angle. If you want to bend on 60-degree angle, you can bend the angle on 60-degree. Similarly, if you want to bend on 70-degree, this particular one side of the angle can be also twisted. Or if you want to bend both the sides, this is like both side of the electrode, and some central region can be bent on particular angles. We can define the radius, psi, other group box parameter, and it will bend your particular structures. Now the bending is done with this particular device. We can zoom the regions. So based on single click, it can also simulate the flexible based device application. And many other possible combinations will also be there, where user can customize, can make the device according to their needs. So this is new file, HZW file with bending is created. And simulation is going on in the background if you want to perform some other things. So let you want to make some nanowire kind of structures. So this is one of the structure where you can select the graphene nanoribbon. You can select, let's suppose, the chiral vectors. This is another structure where you can create the graphene nanoribbon. So define the unit cell of nanoribbon by the chiral vectors. So N and M, bond length. If you want to passivate dangling bond with the hydrogen atom, you can also select the checkbox to enable the passivations and select the chiral vector N and M. By default, the site A and site B, that is carbon elements. If you want to change the element, you can double click on the carbon and the periodic table will open. From there, you can choose the element and change it. And then click on preview. So this is like one of the preview of this graphene nanoribbon cell. This is a preview. We can repeat this in transport directions. So this is like 0x4 carbon based with 1.42 angstrom hydrogen passivation graphene nanoribbon. We have seen the preview, and I can click on build buttons. Now you can click on this build and repeat or redefine these crystals. Let's suppose you want to redefine this crystal in transport direction. Transport is called C direction, horizontal direction. So in this C direction, if you want to repeat 8 times, you can mention this checkbox and click on preview. And it is now repeated 8 times in this particular transport directions. So this is now created the single graphene layer, and then you can click on the build buttons. You can rotate particular angles and zoom by maximizing it. This is one of the graphene layer structure with hydrogen passivation we have created. This is single layer, mono layer structure. We can create the mirror of the same structure, or we can replace the atoms, we can delete the atoms. Many kind of defects can be created as per the needs of the users. Now, once it is done, simulation is going on. If you want to delete, if you want to make the device for this particular graphene layers, what you can do, you can click on convert to device. Once you click on convert to device, select the electrode. I have selected the left electrode. I have selected the right electrode. Default thickness is suggested in G direction, and click on preview. And if you see here, the thickness of the electrode for this boundary condition graphene nanoribbon has been created. And then you can click on this build button. Now the device is ready. The 2-terminal device is ready, where some left and electrode is there and right electrode is there. If you want to add any other element, if you want to add the elements, then what you have to do, you have to select all the elements. So I can click on this select option mode and select all the element and click on this plus button. This plus button will add the element. Add the element means not replacing. We are adding the new element from the periodic table instead of replacing the existing one. So to interact with other element, I can click on the plus sign. The periodic table will open. From there, I can select, let's suppose you want to interact with this lithium. So you can click in this lithium, the lithium element will be selected, and then you can click on the OK button. Once you click on OK, then you can click somewhere, wherever you want to add. Let's suppose I want to click in the center region, and it will add that element. Now, once it is done, the element has been added. Now you can move the position of this selected elements. So you can see here, this is the lithium atom. And how do I know? Left side, you can find there is an option called property tab. So property tab, there is lithium element with their coordinate points. Now, if this lithium atom is making bonding with this graphene sheet, then we can see. So I will select all the neighboring elements and click on this right side, and there is an option called recalculate linker bonds. When I calculate this recalculate linker bonds, if it is making the bonding, then it will make the bonding with the sheets. If the atom is far away with the graphene sheets, then it will not create the bondings. So it is not making the bonding after my clicking multiple times on this layer, on this particular recalculate linker bond options. So what I will do, let me change the position of this element. So I will select this element and click on move button. So this is move atom, where I can move in minus X directions. So how do I know? You can see here, this is vertical is plus Y, right side is Z, and this is G directions. So vertical, horizontal, or whatever, let me take minus Y, so it will take that particular distance. So what I will do, if I want to, let's suppose I want to make so this is like some distance is there. If I want to move this atom with the distance of 0.5 angstrom, I mention it, I edited the value, and it is showing the 0.5 angstrom. I want to move in negative by. So down position, I will click on it and it will change its position. So 0.5 angstrom, it has been changed. Now let me see it is making the bonding or not. So I will click on it and click on recalculate linker bonds. So it is now making the bond with other element, whatever it is making. We can zoom it and visualize it. So this particular atom, it is making this lithium atom bonding. And the similar one, another layer, we can also, graphene sheet layer can also be created and we can simulate. If you want to add other elements or other element from the library, you want to choose some other material. So whatever the other material you want to choose, you can take that particular location and find the type of whatever the molecule or material you want to add. You can add that particular molecules. So I can convert to this crystal to the molecule. So whatever you want to add in that particular previous one, you can simply copy paste. Let's suppose you want to add this one. So I will delete this and add one. And if you want to make, you can copy this element and here you can also add. So any element can be added. Like I added this one. This is here. I can make it center positions. So this is one is center, which we reach to the center position. And then we can move this particular element. And some hybrid functionals can also be created. So you can move in plus by, it will move that, and then move in plus Z, it will move that particular location. So we can create the functionals element by based on that. So I can select this all element and click on recalculate linker bond. So if some bonding are creating, we can create such type of bonding, or any type of structure can be manipulated by the users. Whatever the type of addition you want to do, there are no restrictions where user can do according to their particular needs. If you want to delete particular element or replace particular atom, you can select particular atom and click on this replace elements, and you can replace the N type or P type doping. Select it and it will get it replaced. So I do not have any words to say many more things because it is a very broad software where a lot of functionality are there. But let me show you many other things. If you want to make this device into the transistor level, once you made the 2-terminal device, if you want to convert into the 3-terminal by defining the gate regions, so you can go to the simulator, Nanodcal, and then go to the transistors. In the transistor, you can define the dielectric properties, some dielectric, some thickness value, and that thickness value will add up here. You can see this is the thickness that will also getting add up. Whatever dielectric hafnium, based on the thickness and permittivity, the dielectric type can be selected. And this is a gate. Number of gates are there. You can select the number of gates. Gate voltage 0.1, 0.2, 0.3, 0.4, 0.5. and many more things are there. You can define multiple voltage biasing. And similarly, this is the gate region where you can see this top lines. This region is basically the gate regions. You can increase the thickness of the gate region. Whatever the thickness you want to use the region of this gate, you can increase the thickness region. This is the source voltage biasing. Let's suppose 0.2, 0.5, 0.7, 0.8, 0.9. This transistor source voltage you want to apply with respect to gate different voltage of the gate terminal. So different gate voltage, different source voltage. Click on generate file. Sorry, there is some element need to be added. The basis sets of the element need to be added. So we have to select particular basis sets. So I will go to there. 1 minute. Nanodcal, SCF calculations, and then go to the basis sets type. So this lithium, we have to add the basis sets for lithium. So I want to show you the user defined. Let me see the basis sets for the lithium. So neutral atomic database. So this is LDA, lithium, double zeta, double polarized basis sets are there. So I can select this basis set and it will use it and it will generate the file. Now I will go to the transistor option and select the transistors. And now I will click on generate file. So I have to select the basis sets here as well. So I will go there and there is basis set option. I can select the user defined for the lithium basis sets. So from my database, some basis sets is also available. I will find the lithium LDA DZP neutral atomic database or MATLAB format. The basis sets has been incorporated. You can also add the doping in transistors also. If you want to add the doping, that provision is also there. Click on generate file. Now the file has been generated. So you can see there is multiple file has been generated for different main input file and different gate voltage input files. Whatever the voltage biasing, that is also generated, and whatever the source voltage, drain voltage, or different voltage, the different input files are generated. So we need to run all the input file to plot your IDBD characteristics. So the transistors characteristics, apart from two terminal device, it can also get it simulated. Now, if you see the two terminal device output, you can see the density of state is running the calculation. Main input file of device has been finished their calculation. So device main input file, this one is called the main input file of device. That is completed their job. And right now the density of state is running the job. So I can see some plot for total electron density, which already run in the backgrounds. So this is like total electron density analysis. This is like something plot for this alkylathyl and gold device structures. So based on that particular needs, we can see the view of our outputs, and similarly for Bundy plots. Many analysis is still running the job, but it may take some time. Okay. Similarly, if you wanted to make the device of this particular structure, you want to convert this particular device which I created in front of you, you want to convert into the transistor, then go to the simulator, go to the Nanodcal, and go to the transistors. Relaxation optimization is also there. So you can click on this transistors, and here the default parameters are there. This is the gate voltage, thickness, permittivity, biasing voltage. So if you want to select on single source voltage, let's suppose 0.1 source voltage and gate voltage on different value you want to simulate. So you can click on this and it will generate the multiple projects on different gate voltage. So without any gate voltage, this is one of the input file. With 0.1 gate voltage, 0.2 gate voltage, 0.3, 0.4, 0.5, and constant drain voltage, it will simulate. So dependent on your needs, you can vary, you can change different options. Now simulation may take some time, as you know, it requires some calculation time, but I will show you many other useful information. So if you look into the documentation page as well as our YouTube channel, this is nanoacademic.com main website. I can give you on the chat box also, so that you can look into this website and the documentation page where all the information about device related applications. So you can go down and click on this documentation and tutorials and click on this Nanodcal. Yeah.
Sir, which analysis can be used to predict that this device can be used as a spintronics? What analysis can be used? And how can I say I have a two-terminal device? I want to say this is working on the spintronics field. How can I say that?
So we also have some tutorials. So some based on reference things. If you see this particular tutorial, we have this tutorial on molecular electronics, spin-based devices, zigzag graphene nanoribbon, nickel graphene oxide, DFT plus U, spin orbital interaction, carrier effective mass, complex energy band. These tutorials I can give you. You can read the background informations. Okay. So I want to give you this link. There are so many tutorials are available. You can read it. So if you want to see this, there is some reference is also given there. The reference paper on what basis the software will predict the output. So this is like one of the tutorial zigzag graphene nanoribbons. 4G graphene nanoribbon armchair directions. So they perform the same thing which I have explained in the live demonstration, and they calculated this transmission coefficient with spin up, spin down. So anti-ferromagnetic and ferromagnetic condition, the spin up, spin down, transmission coefficient with respect to energy. And similarly, the other characteristics, spin current you want to calculate. This is one of the tutorial backend. You can see the spin current output. This is for spin current with respect to voltage. Various applied voltage at ferromagnetic FM conditions. And whatever the reference, you can see this is the reference from there. The tutorials are performed based on the parameters. So this is one of the tutorials. Even multiple other tutorials are there. If you see this nickel oxide, nickel graphene interface, this is nickel graphene interface is trying to build and simulate some analysis. Even if you talk about the spin orbital interaction, this is spin orbital interactions. So this is the tutorial part. You can see the general spin, no spin, spin orbital interaction for different material and their informations. If you want to know the theoretical, this is tips and tricks for spin polarized calculation and spintronics. So this based on this equations. This is the background code, background equation. On that equation, it will solve the parameters. You can read these information. I believe it will be very useful for you. Many other information are available on our YouTube channels. So if you look into this YouTube channel and go to this video, You can find couple of videos are already available in different other application, because in 1 day or 2 days I cannot explain full capability. So we have prepared many videos in past on different applications. So I just suggest you to watch these multiple videos on different applications. You can see the transistor characteristics, IDBD characteristics in this particular video, adsorption energy in bulk material, formation energy, stone belt defect of carbon nanotube, or even photogalvanic effect in 2D material waste, monolayer device, thermoelectric properties, conductance analysis, this video. So each step we have tried to cover up. If something is missing, you can also suggest us or recommend us in future. We can try to make video on other applications so that you can effectively understand the capability of the tool on wide range of applications. So you can see these are a couple of other short videos that are prepared on the same software, which I was trying to explain you from yesterday as well as today. So I can give you the link. The people can also watch later this webinar. And I want to show you some other output in the meantime. So I already have some couple of simulated project. So I want to open that project that will help you to understand more insight about the product. So I want to open my existing project which I simulated in past. So if you see, these are a couple of other projects which I work on in past applications. So let me open one of the, let's suppose you are talking about spintronics. So I will open this spintronics. So in the spintronics, this is one of the spintronics. So let me see what they have performed and calculated. If something is there, we will try to see it. Like this is one of the material where what I created in past. This is the density of state, but the spin factor is not included in that. But I will open another one where I will show you some analysis. So let me show you 1 minute. The relaxation is also possible. It will relax all your atomic coordinate points. Let me open another project. Maybe another project I simulated.
Hello, sir. Sorry to interrupt you. So
Yes,
this
please.
Rescu and Nanodcal software, does it run in Linux platform?
Yeah, the calculation can also run on the Linux platform. That is possible. So the interface you can open on the what I say Windows, but Linux is also there. So, but little bit command is there, but you can also run on the Linux. It is supported. Linux is also possible to run the job. We have some packages of the library of this setup for the Linux. So you can run the job. Even parallelization can also be done on Linux platform.
Okay, sir. Because the software that you have asked to download, we are using the executable file, exe file. So those files are not executable.
Yeah, but we have another file, so I can share you another package. You can reply my email. that you required execute that .sh file or something like. So I can also share with you that Linux file.
Okay, sir. Thank you, sir. Thank you, sir. Because from yesterday only, I'm not able to run that the software. That's why.
No problem, no problem. So we can help you later in the workshop so that you can effectively use. So I believe in these 2 days you have learned other things. So these are last time analysis for density of state, band structure, for spin up, spin down. Like you can see this spin type. This is spin up, spin down density of state, and both spin up, spin down at a time on each atoms. You can zoom particular regions and you can visualize on atom wise as well as the projected one, local density of states. And many more tutorials are possible. So even many things I tried to explain, but not everything, because to show everything you require some couple of time. But IV characteristics, transistor characteristics, all are possible in the tool. And if I show some other project, this is like sweet. One minute. Like you can make any other complex based devices. I tried to make this kind of complex devices in past, 4 probe devices. So here the 4 probes are there. You can see the left electrode, right electrode, bottom electrode, top electrode. Similarly, the front and back is also possible. Whatever the type of structure you want to create, you can create according to your needs.
Sir, am I audible?
Yes. You want to?
Sir, yes, sir. What about the spintronics related calculations, sir? In your YouTube tutorial, also you put some video magnetic tunneling junction. What about the spin transport calculation and spintronics related calculations?
The magnetic movement, spin up, spin down, band gap, and what you want. Basically, we also have some magnetic related papers. So whatever.
I want.
Yeah, please.
Spin transport calculation, sir. Suppose I have 2 terminal device or 3 terminals. I want to prove that this device can be act as spintronics. What are the analysis can be used for that?
So as an input, if you talk about the spin, input type, here you can see there are 2 options there. Collinear spin, where spin polarization, the rho value you need to enable. And for general spin, the rho theta pi and spin orbit interaction. These features need to be enabled. And if we talk about the output part, analysis option, the magnetic texture, atomic textures, and spin up, spin down, band gap, and some transport property there, transmission coefficient, it can plot. Thermoelectric property is also there. You can plot the thermoelectric, Seebeck coefficient, ZT, ZT and other analysis you can easily calculate. And if you want to know something more, you can send me one query so that I can look into this later on, and I can definitely reply to you over email.
Okay, sir.
So I have tried to explain many things, but if any participants have want to ask anything, you can please unmute your mic. I will try to answer your questions, please. And those who wanted to see, yeah, please.
Hello, sir. Good evening. So, can you get the information regarding the electronic structure, effective mass, and G factor calculations in your pre-existing projects?
Yes, definitely. The effective mass we also have calculated. So I want to show you 1 minute. My existing things.
Suppose some material we will choose
Yeah.
gallium nitride or zinc oxide or some material we will choose semiconducting material. So
Okay.
can you get the existing data available in your device studio?
Yeah, definitely. We have a lot of data. If you see this particular video, we have created on effective mass calculation. So I'm sharing you this video link, as well as if you look into our tutorials, there is one of the tutorial on effective mass calculations. So if you see this one, this tutorial for on effective mass. So I can refer this link to you. You can read it to there, and I believe it will be very helpful. So you can see the chat box. Two
Sir,
information I share to
sir,
you.
how can we get tutorial link, sir? How can we get the tutorial Nanodcal tutorials?
Tutorials. You can just click on this link which I shared you on the chat box.
Okay.
On the chat box, I have given the link. Click on it. So just type this website, nanoacademic.com. This is the main page, and nanoacademic.com. You can go bottom of this page. Bottom of the page, there is documentation and tutorial option, and Nanodcal option is there on top, and you can see this tutorial is there.
Sir, is there any option to check toxicity of the materials?
Is there any option to check? What did you say?
Toxicity.
Toxicity. I need to find 1 minute. Maybe some paper could be there. I had not worked on it. So if you want to see, if some paper are there, you can simply type toxicity plus Nanodcal. If there is any someone word, then maybe you can find it. You can see this is one of the paper, study on the sensing characteristics of two-dimensional material WT to toxic gases. So they have quoted Nanodcal. So maybe you can also work on that.
Yes, sir. Sir, for writing the paper, how you can assist, sir? In what level you can assist, sir?
Basically, our main objective of this FDP program is just to aware you, to show you all capability of the software, that how the software can be benefited, or how either it is useful or like only how much useful this software tool for you. So basically, our main agenda is just to sell the software apart from the promotional things. Okay.
Oh, this is a wonderful software, sir. Actually, it's very good for research purpose, and it's unique also. But we are looking for the paper and all.
Definitely. So you need to purchase the software because without purchasing, the company will also not authorize you to like publish any articles. Only the demo license or this kind of FDP is just to show you the capability. So if you want to purchase it, you can let us know. We can also provide you the training later on once you purchase the tools.
But I am a single user, sir. I am not an institutional, so it will be very difficult for me to purchase. Is it possible for any single scholars or like that? Any possibilities?
Individual, it is not there, but you can send me email. I can see if any possibility. But I have not worked on single person. We have till now sold to the educational institute or our research lab. No individual till now.
Okay.
So I request to all the participants, kindly please available tomorrow also, because our another speaker will discuss on quantum technology, quantum spin qubit semiconductor devices by tomorrow. So I request please come same time at 5 p.m. I hope you will enjoy the session and you will get more technology product informations. So in future, if you have any requirement for such kind of software, I request you can drop an email or you can call or whatever quotation you required to purchase this tool. Please to let us know. So from my side, thank you to all the participants, and please keep in touch.
Sir, what will be the cost of this software, sir?
Cost is basically dependent on the validity, subscription validity, and the number of license. If we talk about single user, that will cost for 1 year approx 2 lakh plus GST, and for 3 year around 4-5 lakh, and then 6-7 lakh for 5 years. So dependent on budget and the module requirement, we have the packages. So from my side, thank you to all the participants, and please be available tomorrow the same time. We will
Sir,
try. Yeah.
are you providing any feedback link, sir, for GT?
Yeah, and by finishing at the end of this FDP program, you will also get the feedback link, which you can fill up to get the certificates.
Okay, sir. Thank you, sir.
Thank you very much, sir. Thank you. Thank you.
Thank you,
Thank
to
you,
all.
sir.
Yeah, thank you.
Thank you. Thank you very much.
Those participants who joined late this FDP, they can get the recording of the webinar, so you can watch this live playlist. This Impulse Technology, Innovative Research. You can type in your YouTube channel, Impulse Technology, Innovative Research. You can search this one and then find our channel. And this program will also be available live in our live options. So you can click on this live where it will be available here. You can watch the yesterday video recording as well as today's recording available. So people, please participate and watch and subscribe and provide the information. So those who want to work on other application, 2D FAT or other application, the software is capable. I can ensure you. I cannot explain everything within 2 hour session. So you can explore the software and definitely it can work on your particular research which you are working on it. Tomorrow session, just join to work on GFAT application, qubit applications, and many other applications. Thank you once again to all the participants and giving your time to attend these sessions. Thank you. Thank you to all.
Thank you, sir. Thank you. See you, inshallah.